In aviation, the tail is the difference between a controlled glide and a catastrophic stall. Today, we are bringing flight mechanics off the paper and into the air to investigate how different tail configurations dictate an aircraft's survival. For this assignment, I constructed 3 distinct tail configurations from a consistent baseline glider to compare their performance. But to accurately evaluate these designs, we must first define our 3 core metrics. First, static stability. This is the initial tendency of the aircraft to return to its original equilibrium position immediately after a disturbance, like a gust of wind. Second, dynamic stability. This describes the aircraft's motion over time following that disturbance. Does the resulting oscillation dampen out for positive recovery, or does it diverge negatively into a crash? Finally, aerodynamic efficiency. In an unpowered glider, this is dictated by the lift-to-drag ratio, which directly determines the aircraft's maximum glide distance and energy retention. Alright, moving on. Let's evaluate the V-tail configuration against our 3 core metrics. In terms of aerodynamic efficiency, the V-tail is theoretically superior. By combining pitch and yaw controls into 2 angled surfaces, acting as a ruddervators, it reduces overall aircraft weight and interference drag. However, our flight test reveals that this efficiency comes at a severe cost to control. When accessing static stability, the V-tail consistently fails. Because the tail fins are angled at a dihedral, their effective horizontal surface area is drastically reduced. The aircraft simply lacks the longitudinal static stability required to counteract the heavy nose, causing it to drop almost immediately upon launch. Furthermore, the V-tail demonstrated disastrous dynamic stability as seen across multiple test flights. The moment the aircraft enters a pitch oscillation, it lacks the aerodynamic restoring force to dampen the movement. Instead of recovering, it exhibits negative dynamic stability, diverging into an immediate and unrecoverable stall. Next, we analyze the tailless configuration against our core metrics in terms of aerodynamic efficiency. This design is exceptional by entirely removing the tail structure. It drastically reduces parasite and interference drag, allowing it to maintain momentum and glide smoothly through the air. Despite lacking a dedicated horizontal stabilizer, flight testing revealed surprisingly positive static stability. The aircraft achieved its initial equilibrium through a combination of wing sweep and reflex. The upward fold at the trailing edge successfully generated the downward force needed to balance the aircraft's center of gravity. However, its dynamic stability remains a compromise. While it glides well under perfect conditions, the complete absence of a vertical stabilizer means it lacks the physical surface area to rapidly dampen out lateral directional oscillations. If disturbed by a crosswind or an uneven launch, its recovery behavior is sluggish compared to a traditional empennage. Our final evaluation brings us to the conventional tail. Looking at aerodynamic efficiency, this design carries a theoretical penalty. The multiple intersecting surfaces of a dedicated horizontal and vertical stabilizer create significant interference drag compared to the V-tail or tailless designs. However, flight testing proved that stability preserves energy. In terms of static stability, the conventional tail was unmatched. The dedicated horizontal surface instantly trimmed the wing's pitching moment, while the vertical fin provided a strong weather vane effect. Most importantly, it exhibited exceptional dynamic stability when subjected to minor disturbances. The dedicated empennage provided strong restoring forces that rapidly dampened any pitch or yaw oscillations. This positive dynamic stability prevented the aircraft from bleeding off kinetic energy in stalls or lateral slips. ultimately resulting in the longest and most efficient practical glide performance. To conclude this investigation, we must determine which design to adopt for a final aircraft. While the V-tail and the tailless configurations successfully reduce theoretical drag, our flight testing proved that aerodynamic efficiency is useless without control. Therefore, I will adopt the conventional tail design. The minor penalty of increased interference drag is vastly outweighed by its superior static and dynamic stability. By actively dampening oscillations, the conventional tail prevents the aircraft from bleeding off kinetic energy during stalls or slips. It maintains the optimal angle of attack, proving that robust control surfaces are the true key to maximizing practical flight performance.